Hello, everybody. My name is Gordon Watts from the University of Washington in Seattle. I'm here to talk about the heptables project, which is part of IRIS HEP, a software institute funded by the National Science Foundation. To start, I'd like to give a little bit of context discussing particle physics data in the Python ecosystem. The Python programming language is expressive, readable, and concise. However, it is not fast. This is because it is both dynamic and interpreted. The scientific Python ecosystem has addressed the speed issue with a library called numpy. This library replaces loops over arrays with compiled code. Consider, for example, this table of values, one row for every event, a column for each attribute. So for example, the first jet PT. If the first jet PT represents an array, the first expression will double the jet1 PT. This first expression is an implied loop in Python. It executes in Python and is unfortunately slow. Second expression, array, is an object in numpy. 2 times the array, using operator overloads, is pushed down into compiled code and executed very efficiently rather than in the Python interpreter as with the first expression. Unfortunately, particle physics data is not a rectilinear table as I was just showing. Instead, it tends to be more like arrays of arrays. For example, here we see a list of attributes, jet, PT, eta, phi, electron, etc., missing ET for each event. Each row again is a single event, but notice you can have an arbitrary number of jets or an arbitrary number of electrons. NumPy does not efficiently represent this data structure. Awkward array was created to address this impedance mismatch. Using many of the techniques and built in part on NumPy, it is designed to efficiently handle non-uniform arrays, like the data structure depicted here. While expressive and fast, this model of analyzing particle physics data does face some limitations, especially when requirements for the high luminosity LHC are considered. As you can see from the plot, the increase in luminosity is going to be dramatic. This will be fantastic for physics. However, it is going to present scaling issues for any analysis that we do. To answer this, the analysis will need to be distributed. Analysis will span multiple types of data access systems. This will be particularly true if we want to reduce disk space usage. I'll mention this a bit more in the next slide. Finally, both awkward array and numpy use an immediate execution model. This model means a large number of temporary data structures can be created during the execution of a complex expression. I would like to say a few more words about spanning systems. One of the goals of modern analysis is to reduce the amount of time it takes to go from an idea to being able to look at something like a histogram. Currently, this involves accessing data on the grid, downloading it locally, and then finally processing it to produce the histogram, an operation that can take days or maybe longer sometimes. Consider this processing chain. The physicist types in a query to build a histogram. That query is then split between ServiceX and Awkward. ServiceX is very good at taking experiment reconstructed data and extracting and filtering it to produce columnar data. Awkward is very good at taking that columnar data and producing a histogram. Further, Awkward is amenable to being run on a distributed cluster, for example, a cluster managed by Dask. All of these services together should make it possible to process large amounts of data with very short turnaround times. However, ServiceX and Awkward do speak different languages. It is important from the physicist's point of view that there be a single uniform way to express the physics that they would like to see rendered in the histogram. So it's logical to ask if anybody has solved this problem before. Let's look to Dask, which has deep integration with the NumPy library. Dask works by recording the operations the user wishes and then distributing it across multiple machines and processes, and finally aggregating the results of that. Dask does this by building a computational graph of the user's query. Here, our proxy points to a representation of 2 times the array. This computational graph is steadily built up with increasingly complex additions to the expression. Finally, when the user is ready, they use the compute method, which turns the compute graph into an actual result. In this case, an array where all the values are twice the original array. We can summarize this in the following steps. First, recording the operations and building the computational graph. Second, translating the operations to the target system. So shipping the expressions to each of the computers and chunking the data. And finally, executing the expressions on those individual chunks in parallel, and then aggregating the results and returning them to the user. So the first step is recording the computational graph. Start with a token that represents a source of data. For example, a grid data set. We set this equal to array. This array we then multiply by 2, generating our proxy. The package DataFrame expressions has a DataFrame class which represents that token. DataFrame supports operator overloading, so when it's multiplied by 2, it knows that it must generate a new proxy which represents the original array but multiplied by 2. To build this computational graph, DataFrame supports standard mathematical operations, numpy operations through a dispatch mechanism defined as a standard part of the library, method calls and property calls on the data frame, arbitrary slicing, and an experimental interface for many of the awkward functions. DataFrame Expression's only job is to build this computational graph. It does not perform any execution or even reason about the operations that it's recording. The execution is taken care of by a second package called heptables. As a quick example, let's render our proxy from the previous slide. When the user calls the makeLocal function, it kicks off the process of rendering the data locally. Heptables first finds the token representing the original data, this AST data frame in this particular case. Heptables then looks at its list of backends to decide which is the best backend to render that particular node. Heptables then traverses the compute graph back towards the final result, looking for all operations that can be executed by the same backend, in this case, the ServiceX backend. Once it's accumulated all the nodes that can be executed by the ServiceX backend, it asks the backend to render the data as awkward arrays. In this particular case, this is the final answer, and so the awkward array is returned in local memory to the user. This is an example of where a single backend can execute every operation in the requested tree. Of course, multiple backends may be required. For example, ServiceX cannot execute every possible operation that Awkward supports. As a very simplistic example, let's pretend ServiceX cannot do multiplication. Heptables will start just as it did previously, but it will discover that the ServiceX background can only execute that first AST data frame. To execute the multiplication, it will then go back to its list of backends, discover that the awkward backend can execute the multiplication node. It will then pause, waiting for the ServiceX backend to render the data. Once that's available, it will use the awkward backend to render the multiplication by 2. Just as before, this data will be returned as an in-memory awkward array and sent back to the user. An arbitrary number of backends can be handled like this. Another thing to note is that a backend will accumulate a potentially complicated compute graph. Operations can be formed on the compute graph to optimize it, fusing operations where necessary, for example. So heptables currently exist as a prototype. For example, I have pasted various cells from a Jupyter notebook, which scans some Atlas Z2EE Monte Carlo, performs a cut on both eta and PT, and then plots the PT as you see here. The prototype is finished. ServiceX and an in-process awkward backend exist. Only simplistic expressions are routed to ServiceX. Histograms and other types of aggregation are done in process. I've used it in some simple Atlas Monte Carlo analyses for long-lived particle searches. However, it has some serious limitations. The awkward integration is insufficient currently. The code required to do complex multi-object operations, for example, matching jets and tracks, is not readable in the current version of the system. Further, only simple expressions can be sent to ServiceX, which leaves much of its power on the table. Currently, a rewrite of the ServiceX backend is underway to support much more complicated queries. The awkward backend needs to be rewritten to support Dask clusters. A prototype of this already exists outside of the heptables package. A strategy to better support awkward arrays' standalone functions must also be developed. Finally, it should support rendering data in other forms besides histograms or awkward arrays that are in process. For example, distributed Dask arrays. This will allow it to play better with other packages in the scientific ecosystem like Seaborn.